Alrighty guys, looks like we're doing Ultimate Tic Tac Toe. Ultimate Tic Tac Toe is just like regular Tic Tac Toe, but times 9. Each square has its own Tic Tac Toe board, so when you win a small game, you win that square on the big board, and winning 3 big squares in a row wins the game. Seems pretty easy, right? The twist is that the square that you play in on the small board forces the opponent to play on that corresponding big square on their turn. So for example, if my opponent decides to play here on their turn, I would have to play on this board on my turn. A couple of minor but important rules. First, if a small game ends in a tie, that square counts for no one. Second, if your opponent forces you to play in a big square that is already won or tied, you can choose to play in any open square. Third, if no one gets 3 in a row on the big board, then the winner is the one who won the most squares. Okay, now that we all have a feel for how the game is played, we're each going to get 1 week to build a bot. Once we're done, we'll pit them against each other and see who came up with the best strategy.
Okay, so I know I'm supposed to build a bot for this game, but I don't really know anything about AI. So I think I'm just gonna make something that would just play like I would. And I've played a grand total of 1 game, so I am a total expert. Alright, so my gut tells me that there are a couple of things that the bot should do, depending on the situation that it's in. The first is to avoid losing, obviously. So any move that would put the opponent in a position to instantly win the game is probably not a good idea. So if I were to move here, then the opponent would get to play on this board and then complete that 3 in a row to win the game. So that means that original move was not a good move. Those moves get put in the trash. So then, if you can win a small board, that move is good and you should play that move. If there are consequences, well, let's just not worry about that. Then if I can't win, I should at least not give the opponent a move that will let them win a small board. So those moves also go in the trash. From then on, it's a little less obvious what move we should play next. But I guess we should avoid letting the opponent play on a board where they already have a mark, because that would give them 2 next to each other. And 2 in a row is just 1 away from 3 in a row. So I also want to try and put 2 next to each other, for my own personal benefit. So I'll just choose a move which tries to do both of these things. But if there aren't any moves like that, I'll just do one of them. And then if none of those work, we just have to choose a random move. And God forbid if there are no more moves left, we're gonna have to start taking moves out of the trash. And I hear you saying, what about blocking? And to that I respond, that's way too complicated, and I'm not gonna bother. Alright, time to code. Alright, I have a genius idea that'll completely throw their bots off. I realize that sometimes you can have these winning chains where, let's say, your opponent plays a move that wins a board, but also gives you the ability to play a board that will let you win. So really, we just traded winning boards. If they don't look ahead, they won't see that coming at all. Okay, I have the bot coded. And that's an illegal move. Alright, it works, look at it go. So it's currently playing itself. And not anymore. Alright, I think it works now. So let's just try playing against it. Well, this thing is dumber than I thought. At least it beats a random bot. Although it's kind of concerning that it can sometimes lose to a bot which literally plays random moves. I wonder what would happen if I removed the winning chain thing. It's actually better without it. Fine, why did I even think that would work? Alright, so that's my final bot. I have absolutely no faith in its success, but my time is up, so there's nothing I can do about it now. I just hope these guys don't try hard this.
Alrighty guys, here's the thing. I didn't really want to make this bot, but I'm getting roped into this anyway, and I really want to smoke Amped out of the water. So we're going to be pulling out all the stops for this one. So here's the plan. I somewhat remember learning about an algorithm called Minimax, used for solving 2-player games by looking at future board states. In theory, this algorithm should be built for a game like this, so I'm going to start by refreshing my memory on this guy. Be right back. Alright guys, after some painstaking research trying to understand the min-max algorithm, I definitely think it's going to work for a game like Tic Tac Toe. So let me quickly explain it before we jump into the coding. So the min-max algorithm starts by taking the current board position and generating what are all the legal moves a player can take from that board position. In this sense, it's kind of like a tree, where the initial position is the root of the tree, and one level deeper are all the leaf nodes, which represent future board states. What we're going to do now is just evaluate each of these board states with a function we pass, and basically just pick the max. Whatever the max is the best move for our initial player. But that's the one level scenario, and min-max's real strength comes from the ability to go deeper than one level. So let's explain the two level scenario and see what the differences are. So in the two level scenario, we basically do the same thing, right? First level generated the same way, but for the second level, we have a couple key differences. First, when we're generating all the legal moves that we can take, we have to do it from the lens of our opponent because it is technically their move. Now, once we have all the legal moves of our opponent, we get the second difference of taking the min leaf node instead of the max. The reason we're taking the min is because we're evaluating these board states from the perspective of our opponent, and the min move is our opponent's best move, and it's also the worst move for us. So in this manner, min-max is an algorithm that's just alternating between picking the best move for ourselves with a max operation and picking the best move for our opponent with a min operation. And we can go back and forth however many layers into the future that we decide. So that's the plan. A little complicated in theory, yes, but it should be really powerful. So let's jump into the coding. And boom, it's done guys, right? Not really. While we have a basic implementation of min-max complete, we need to optimize our code a bit to maximize the depth of our min-max tree. That way, we're looking at more future board states and actually have a better bot. To do this, we'll use an existing algorithm called alpha-beta pruning, which keeps track of the best maximizing and minimizing move for each player. This will allow us to trim board states that cannot yield a better move than a move that has already been explored and tracked. This should yield some impressive time savings, so we're going to spend a day or two trying to implement this. Alright, now that we have a semi-optimized min-max tree, we need to spend some time focusing on how to evaluate the board state for our min-max algorithm. So far, I've been returning random values when evaluating the board state, meaning that even after 5 days of coding, our bot is basically playing like a random bot. Instead of returning random values, we need to come up with some heuristic or number value that explains how good or bad a board state is for the current player. A couple of quick guidelines we want our heuristic to follow is that bigger values are better for ourselves. In addition, we want to split our heuristic into two parts. One heuristic for the small board, and one for the final board that combines the values from the small board heuristic. Let's start with a small subboard. To win the subboard, we have 8 possible winning combinations of 3 in a row that will allow a player to win a board. To measure how close a player is to winning in a specific manner, we will set up a formula that depends on how many of our symbols we have in this column. Like here, this column has 1x, so it gets a score of 1, while this column has 2 x's, so it gets a score of 2. Importantly, if a column is blocked like this one, it will receive a score of 0. Naturally, we can loop through each of these 8 winning combinations for each player, see how close a player is to winning in this specific manner, and then add each of these combinations to get a winning heuristic number for each player. Run this mystery code here that I don't really want to explain, and we'll also have a heuristic value for the tie. Finally, we have 3 values, and if we normalize them, we'll have a probability of each player winning that we can send to our final big board and use to construct our final heuristic. Now, to determine the final winning chances for each player on the big board, we can take some principles from conditional probability. The big board has 8 potential winning lines, and to calculate the likelihood of a player winning in a particular way, we multiply the probabilities of winning each of the 3 small squares in that line. Summing up each of these values across all 8 lines gives us the chances for each player winning. To obtain the final heuristic value of the board, we then subtract player X's total probability from player O's total probability. This value represents the relative strength of each player's position on the big board and is a comprehensive assessment of the board state. The bot is finally done. Alright, now that it's done, let's see how this bad boy shapes up in an actual game. Hey, look, that's cute. The bot's about to win. Huh? Okay, it looks like the bot can win here too. Are you... I am absolutely seething right now. You guys saw the bot miss 2 wins here, right? So logically, hey, there's a bug in the code. Well, after an hour of debugging, no, there is no bug. No, the bot just knew that no matter what I played, it was guaranteed to win. So not only did the bot decide to troll me in the game, it also wasted an hour of my life debugging a non-existent bug. I'm done. This bot is ridiculous. It's going down. Oh my god, I've done it. I have gotten a win. Or I guess, tie, same thing. I'm done. I'm calling it quits while I'm ahead here. Overall, guys, this bot seems really good. I've played it 20 times at this point, and I haven't won once, and I've only gotten 1 tie. So I'm excited for his chances, and definitely ready to kick some ass.
Alright, so I think some sort of tree is probably the best way to approach making a bot, but Minimax has a pretty big flaw when it comes to evaluating positions. So let's take this Tic Tac Toe board for example. Minimax explores each of these possible moves at an equal depth in the exploration tree, which is a great way to start, but a better way to approach this would be to spend more time exploring moves that are more promising. This seems pretty convoluted at first, but there's actually an algorithm that already does this, called MCTS, or Monte Carlo Tree Search. Okay, but honestly, I have no idea how this works. So I'm going to embark on a profound exploration of the intricacies inherent with the algorithm, endeavoring to grasp its essence with unparalleled depth and nuance. Psych! Who am I? This guy? No. To actually break down the components of MCTS, research papers are going to be key. So, after reading through a couple of these papers, I finally got the basics down. Okay, so there are 4 key components to a single step in the MCTS algorithm: selection, rollout, backpropagation, and expansion. Okay, so our initial tree starts out with just one node, which represents the current position of the board. This is called the root node. On each step, one more node is added to the tree, where each new node represents a move to a new position. For example, if I go from this node to this node, it means I played this move. We also keep track of how many times each node is won, and how many times each node has been visited in total. I'll explain what this means later. Oh, and we also save which player needs to play next from that node. In selection, we start from the root node and keep moving down the tree until we find a leaf node. To do this, we use a formula called UCT to select the best child node until there are no more children to select from. Then, from this leaf node, we perform a rollout. We start by taking the position of our selected node and then pick random moves for each player until we reach a position where X wins, O wins, or it's a tie. This leads us to the backpropagation stage, where we take this result and update the leaf node and its parents all the way back up to the root node. Keep in mind that we only add a win to a node if the win corresponds with that node's player. Finally, we expand our original leaf node from selection. This involves getting all the possible future moves that that player can play and adding a new node for each of those moves. Now that we've done this once, we can do it again and again until we've done it tens or hundreds of thousands of times. And once we're done running this, we play the move with the lowest win rate for our opponent. So after that explanation, I'm completely drained, so I'll save the coding for tomorrow. Okay, so I did a bit of coding off camera, and theoretically this should work. Well, that's helpful. I guess we gotta debug some stuff. Makes sense. Huh? No way. I think I'm losing my mind. What the actual Okay, so after a family-friendly coding session, we finally have a working bot. Now, according to the forums, the top bot should be getting at least 250,000 simulations per second, so... Yikes, this is a problem. But first let's test our bot against some other people to see how well we do. There's a site called Coding Game that has an arena for people who want to develop their own bots, and there are 4 leagues ranging from bronze to legend, so we can test to see how well we perform against different tiers. So we wrecked bronze and silver, but we kinda seem stuck at gold. The job isn't finished yet, but we're getting there for sure. The next thing we have to do is optimize the code so it runs faster. Luckily, I already coded this in C++, which is one of the faster languages, so I won't have to rewrite the whole thing, but there are still some key issues that are making this run too slowly. Of course, there are small things like our slow random number generator, which we can replace with a fast pseudo-random number generator that only uses some bit shifts, but there are some larger issues. The first fix is typing. For most of the variables, I'm using a traditional integer to store data, which takes around 4 bytes of space. However, a lot of these values will never be large enough to need that much space, so we can use a smaller data type, like an 8-bit integer, to save on that space. Another issue we have is generating a set of legal next moves given a specific board state. This is needed for both the rollout and the expansion stages, so making this efficient is pretty important. For every small board state, we can pre-calculate a list of legal next moves before we even start the MCTS algorithm, and then access those pre-calculated lists whenever we need a list of next moves. We can also do this for checking winners or losers for all possible end board states. And our final fix here is creating millions of blank nodes before we even start running the algorithm. This way, we can save time by not creating nodes during the process and instead only forming connections between the nodes we already created. Okay, now that we're done with our optimizations, let's see if we have any improvements. And looks like we almost 10x'd our performance, but there's still more work to do. Something I completely forgot to address until now was the UCT equation. So in selection, we use this formula on each node and pick the node with the lowest UCT value. You see this little c over here? Well, this is a constant, and apparently picking the right number for this is extremely important. I've been using root 2 up until now just because it was mentioned in a couple of papers, but this is probably not the best. So after a bit of testing, 0.4 to 0.5 seems like a pretty good range for this. Okay, so when we simulate a rollout, we're currently playing moves completely randomly, but to make this better, we can actually add a check to make sure the rollouts play a winning move whenever possible. This check doesn't really slow down the algorithm, but it makes the rollouts a lot more accurate. Okay, so the combination of efficient code, fixing our C value, and using smart rollouts not only got us to Legend, but boosted us to the top of Legend. We ended up finishing at around 35th place out of over 8,000 people, which places us in the top 0.5% of all participants. I think we're ready for the battle.
Alright guys, all of the bots have been coded, so now it's time to put them to the test. Each bot will compete in 1,000 matches against each other, and the bot with the highest number of wins will be declared the overall winner.
Alright, before we view the results, let's watch a couple games. Wait, you played in the corner.
Oh, easy.
Okay.
Okay.
It's actually looking really even right now.
Oh my.
Okay. Okay, I can't lose.
Wait,
this.
dude. Well,
There is.
oh,
Hey, I'll take a tie.
oh, the rematch. Okay.
Oh no.
Oh, give me that.
Oh, no. Okay, this is me. That's okay. This is recoverable.
Wait a
This is
second.
recoverable. I'm so good.
Wait, what is going on?
What the hell?
Oh gosh. What is happening in this game, dude? I can't even.
Dude, your
I don't understand
broken,
it.
Dude. Wait, I win?
Base won 5 boards, Minimax won 3, so
I have yet to get a dub.
could get a win here.
Oh yeah. Oh yeah. You're right. You do think. You would say
Oh,
so.
no.
Let me tell you, I am winning this game.
Where?
But I
Where are
can
you
tell.
winning this game? I
What
don't
fucking
see. I don't
universe?
think we're seeing the same thing.
All right,
Kinda
now I'm just
giant.
begging for a win at this point.
Going first, so that is an advantage.
Okay.
What?
Oh fuck.
Oh,
That was
Oh.
a good start.
You know, maybe there's a bug in my bot. Maybe I can
Okay,
get a win
alright.
here.
A little better. You made up some ground.
pretty even. Okay. Okay. Winning a big board.
Yeah, this is good.
Okay, winning 2 big boards. Okay.
I'll be honest, this doesn't look
Oh
good.
my god.
This does
Let's
not
go.
look good
Let's
at
go.
all.
What?
This,
What?
Oh my god! Wait.
Wait, what?
wait,
What?
you've been screwed.
bro.
How many games am I gonna play, dude?
Oh, wait.
This is a win for Minimax.
This is
Oh,
raps.
what?
No, I went from like 100 to 0. Another
Oh, yeah.
rematch,
Oh, this was maintaining.
Another win?
There's a guaranteed win. There's a guaranteed.
another win.
What happened?
What? Is it bots? Did it just think
Don't tell me that even when I'm gonna win, it decides to just not play, dude. As long as it decides to. Okay, there we go.
Okay, so for each game played, a win counted as 1 point, a loss counted as 0 points, and a tie was half a point, so the best possible score would be 1,000 points, one for each game. Now, time for the results. In last place, we have HackersBot with a very respectable score of 6 points. Big surprise here. Next, we have CabsBot with a total score of 576. And finally, our champion, with an impressive final score of 918, we have me.
So overall, MCTS was the best algorithm, but both Minimax and MCTS play as well or better than a human. Although this really isn't surprising since they can both see much further into the future than any normal human could. But MCTS has the edge, since it's able to optimize its runtime by prioritizing more promising moves. So after coding our bots and watching them play, we learned a couple of things that you can apply if you're playing this game against others. Number 1, if you're going first, play in the center of the big board. If you're going second and your opponent plays in the middle, you should play in the corner of the center board. Keep in mind which boards are most important. So the middle board is the most important, followed by the corners and then the edges. Try not to play a move that gives your opponent the ability to play anywhere on the board. Don't hyper-focus on winning small boards. And lastly, look 100 moves deep into the future and calculate every possible future board state.